Okay, hello everyone. I hope you are doing fine. Sorry for not being able to attend the lecture last Thursday because of some health issues. Uh, last time we were talking about the scheduling algorithms, process scheduling. We had covered first come first served scheduling algorithm, and then we were talking about shortest job first algorithm. But remember, we shared that starting shortest job first scheduling algorithm, it actually schedules processes based on their next burst, right? Next burst time. So, but the issue is that we cannot know the next CPU burst of a process without actually running it. So, if we cannot know it in advance, then the only thing we can do is to estimate the next CPU burst of a process, right? And for that, we can use the exponential averaging to estimate the next CPU burst. So, for example, let's say if we denote the length of the nth CPU burst of a process. When we say nth CPU burst, it's again, remember we said that the lifetime of a process, it consists of different interleavings of CPU burst and IO burst. So like let's say here you have CPU burst, and then this empty block is indicating, let's say, IO burst. Then you have another CPU burst of a different length, right? And then other IO burst maybe of a different length, then another CPU burst, and so on, right? So this is, for example, let's say this is your 0th CPU burst, this is your uh, first CPU burst, this is your second CPU burst, and so on, right? So uh, what we want to do is to estimate the length of a CPU bus, next CPU bus, right? So let's say that Tn denotes the length of the nth CPU burst, right? So this is, and by Tn we mean the actual length, right? For example, let's say this is T1, right? This is T1. So we want to, so T1 indicates the actual CPU burst, uh, and ta n plus 1 denotes the predicted value for the next CPU burst. So for example, if T1 is the actual value, let's say the actual value is equal to, I don't know, maybe 10 time units. And ta will be the value, ta1 will be the estimated value for this burst, right? Which can be anything depending upon how we are finding the estimate. So ta n plus 1 denotes that predicted value for the next CPU. So if based on T1, we want to pay based on T1 and ta1, we want to find ta n plus 1, which is basically 2, which is the estimated value of the next burst, so the second burst, CPU burst, right? Assume the first CPU burst is burst 0 and its length is T0. So the actual value is T0. Like for example, let's say we are for the first burst, we are saying the actual, whatever the actual value was, we are indicating it by T0. And then tan denotes the previous estimate before Tn, right? So then we can use this formula or equation to find the estimate of the next burst. Ta n plus 1 is equal to alpha times Tn. So the estimated value of the next burst is equal to alpha times the actual value of the previous burst plus 1 minus alpha times estimated value of the previous burst, right? So in this equation, if alpha is equal to 0, if we put alpha is equal to 0, then it's mean that we are saying that next estimated burst value is equal to previous estimated burst value, this one, right? So here we are essentially saying that recent history does not count. Recent history does not count mean we are actually saying that for every burst, our estimated value will be same, right? So, and it is not affected, whatever we compute the estimated value for the next burst, it is not affected by the history or by the actual burst value of the previous burst. So, and if alpha is equal to 1, if you plug alpha here equal to 1 in this formula, so you will see that this will become equal to 0, right? and tau n plus 1 will be equal to Tn. So we are basically saying that the estimated value of the next burst will be equal to the actual value of the actual length of the last burst. So only the actual last CPU burst counts. So these are two extreme situations where you are setting alpha equal to 0 and alpha is equal to 1, right? Usually we have alpha between 0 and 1, for example, 0.5. Now let's have a look at example. Let's say that uh, we have a process for which the tau 0, which is basically the estimated length of the first burst, is 10 millisecond, and at the same time we know the actual length of the first burst, which is 8 millisecond, actual length of the second burst, which is CPU burst, which is 16 millisecond, actual length of the third CPU burst 20 millisecond, and the actual length of the fourth burst CPU burst, which is 10 millisecond, right? So, but we know only tau 0, the estimated value of the first CPU burst. Now we want to find tau 1, which is the estimated value of the first burst, estimated value of the second, and estimated value of the third CPU burst, right? So how we can do that? If we know, if we use alpha equal to 1 by 2 or half, then you can simply plug in the values in this equation. If you plug in the values, so if you put n equal to 0 here, so tau 1 will be equal to 1 by 2 times 8. What 8? So here you are saying t is equal to 0, right? So when you plug t 0, we know it is 8. So we are simply plugging this 8 here plus 1, and this is alpha times 10. What is 10? It is tau 0, right? Tau 0. And what is tau 0? We already know it. So tau 0 is 10 milliseconds. So we are just plugging it here, and you will do the math. You will find that tau 1 is equal to 9 milliseconds. So now we have, for the second burst, we have actual length of the burst and also the estimated length of the burst. Now we want to find the estimated length of the burst for the second burst, or for the index n equal to 2, right? So tau 2 is equal to what? Alpha times T1. So what is T1? It is 16, right? So we are just plugging in the value here. 1 times 16 plus 1 times tau n, which is basically tau 1. So tau 1 was 9. So we are just plugging in the value here and you will get 12.5. Is it clear how you can calculate the estimated value of the length of a burst if you know the estimated and the actual length of the previous burst? Any questions?
So for the first time, our estimate is 10 milliseconds and our measured is 8 milliseconds. Is that
Yes.
okay?
So we are just, so this was our first estimate of the first burst, and this is what we measured actually after running the process, and we
Okay,
found.
so we make an estimate, we run it, and then we compare the results.
Yeah, so we make an
Okay.
estimate, we run it, and we found that actually it took 8 milliseconds for the first burst, not 10. But now, once we have these two things, T0 and tau 0, based on this formula or equation, you can find the tau 1.
All right.
And so tau 1 is now 9, and then you run the process for the second CPU burst, and you measure it and it is 16 millisecond. So you say, oh my, there is difference between my estimated value and the actual one. So 9 minus 6 to 16 minus 9. So there is like difference of 7 milliseconds, but you have an estimate. Now, after that, using the estimate for the second bus, like tau 1 and T1, after using these two, you can find this estimate for the next bus, which is 12.5.
Hmm.
Okay, you just plug into the equation, makes sense. Okay, yeah. So, okay, I have a question. I missed where we got alpha from. Where does 1 by 2 come from? So alpha is just a weight. Like it is your decision what value of alpha you want to use. Like if let me go back here. So here alpha. this component is basically uh, the weight where you are assigning weight to the actual measurement of a bus Tn, and here you are assigning weight to the estimation of the of a bust like tan, right? Now it depends upon you, like what weights you want to assign between 0 and 1, right? So if like you as there is no, like, how to say, maybe there is some mechanism to find what is the maximum, or not maximum, what is the optimum value of alpha, but the extreme cases are when you set alpha equal to 0 or alpha equal to 1, but usually you can set alpha equal to 0.5. In this, here we are not covering mechanism about finding what is the optimum value of alpha, and I don't know what is how you can find the optimum value, but here we are assuming that it is a given information. Okay, okay, got it. Okay, so with that, any other questions before we go to the polar quiz? No? Okay, so with that, let's go to the quiz week 9, day 1. Where is that? Day 1, quiz 5. Okay, yeah, go ahead and solve this one. I will not give extra time because we need to cover the course material, so please finish it in 45 seconds. Okay, uh, so you only need to plug in the values, right? So you already for finding the tar 3, you need to know tar 2 and T2, right? So you know both of those values. You simply plug them in the formula and you get 16.25 as tar 3. Okay, so what is tar 4? Uh, this is our next. Oh, question 6. Yeah, go ahead. 45 seconds. Yeah, again, so you just simply need to plug in the values of T3 and tar 3 and do the calculation. You will find 13.125, right? So the next CPU burst is estimated to be 13.125. So the CPU burst for like tar 4, the fourth CPU burst. So after the burst is executed, it is measured as T4, right? And we will like simply here we will find, okay, now we know T4. So based on T, we know T4 and we know that tar 4, then we can also calculate the next estimate of the next burst. Okay. Example. Assume we have the following processes. Find out the finish time, waiting time, and you need to find three things, right? I hope you guys remember what is finish time, how you find the finish time, waiting time, and turnaround time from the last lecture. So find out the finish time, waiting time, and turnaround time of each of the processes for the SJF, shortest job first scheduling algorithm. So I'm releasing the poll. Question 8. Yeah. And you have 120 seconds. You don't need to fill in the blanks, just do on your notebook and you can note the values and you can then compare with the solution, which I will show you in next slide. I'm giving you 15 more seconds. Okay, uh, let's stop here. And okay, so do you want me to go to OneNote and explain how to get these numbers? Is there anyone who want me to explain? Uh, yes, please. Okay. Okay. So then let me simply copy this table and go to OneNote, right? This was shortest job first, right? So um, this is my, let's say, timeline. And here I'm drawing 0, 5, 10, 15. So these are arrival times, right? So A is arriving at 0, B is arriving at 5, C is arriving at 10, and D is arriving at 15, right? And okay, so this is, so at time 0, I don't have any other candidate, only A is the candidate. So, and this is shortest job first. So I run A for 30 time units, right? So A runs for 30 time units. Now I am done with A, right? So after that, there are three ready processes, B, C, and D. Which one of them has the smallest CPU burst? D, right? So I run D for 10 time units, right? So I am done with D. And after that, I have two candidates, C and B and C. Which one has smallest C, smallest burst time C? So it runs for 12 time units. So 52. Left with B, which runs for 20 time units. So 72. And now I'm done with all of them, right? So finish time, let's say A, B, C, D. I'm writing F for finish time. What else we had? Waiting time and turnaround time. So finish time for A is not 30, right? For B, 72. For C, 52. And for D, 40, right? Now waiting time for A, waiting time is it arrived at 0 and it started at 0. So waiting time is 0. For B, it arrived at 5, right? And it started executing at 52. So the waiting time is this one, right? So 52 minus 5, can you do the math? So 47, right? And for C arrived at 10 and it started executing at 40. So the wait time is this one. So 40 minus 10, 30. Okay, I will check your message. Just give me 1 minute. And D arrived at 15, right? And it started executing at 30. So 30 minus 15, 15. Okay, what is the message? Let me check. How do you choose the order of the process again? Is it by CPU bus except for A? Yes, it is by CPU bus, but not for except A, for A, even including for A, because at time zero, so remember at time zero, w- which processes we can choose? Only we can choose process A. Why? Because other have not yet arrived. They are not yet in the ready queue. Because B arrives at 5 in the ready queue, C arrives in the ready queue at 10, and D arrives in the ready queue at 15. So when at time 0 I need to make the decision, there is no other candidate. Only A is the candidate. So I pick A and I run it for 30 time units because 30 is its CPU burst. Do you get your answer? Okay. So, and turnaround time. So turnaround time is that from the time where the process arrived to the time where it gets completed. So for A, it is A arrived at 0, right? And it get completed at 30. So 30 minus 0, 30. So let me use a different color just to indicate that because there is so many black lines. So the turnaround time for A is this one. So it arrived at 0 and it completed at 30, right? For B, it arrived at 5 and it completed at 72, right? So this time difference. So 72 minus 5, 67. And for C, it arrived at 10 and it completed its execution at 52. So 52 minus 10, 42, right? And for D arrived at 15 and it completed its execution at 40. So 40 minus 15. So 40 minus 10, 30, 30 minus 5, 25, right? So I hope I have correct solution. Yeah. Okay. Any questions? No? Okay.
Makes sense. Thank you.
Okay, you're welcome. Okay. Uh, Now let's talk about the next scheduling algorithm, which is shortest remaining time first. Actually, it is simply preemptive version of shortest job first, the scheduling algorithm which we have just covered. So shortest remaining time first is simply preemptive version of shortest job first. How? Because in shortest job first, we were not doing prevention. We were not doing prevention. What does it mean? It means, for example, here, if you see in this figure, so we like at 0, we said, okay, there is no other candidate, only A is the candidate, and we scheduled it for 30 time unit, and it completed at 40, not 40, it completed at 30, right? But between 0 and 30, other processes became ready. Like became ready, entered in ready queue at 5, C entered at 10, and D entered at 15. But still we allowed A to complete it burst, right? These other newly arriving processes B, C, and D, they didn't preempt preempt the process A, the execution of the process A. Process A was allowed to complete its execution. So shortest job first is not preemptive. So for example, what is the burst time of A? It is 30, right? C arrived at B arrived at 20, right? So no, sorry, B arrived at 5 here, right? But at this time, how much remaining bus time we have for A? 30 minus 5, 25. What is the bus time of B? 20. So B has shorter bus time as compared to A, but still we allowed A to complete, and it completed at 30, and then after that we looked for the process which has the shortest bus time, right? So that is not the case for shortest remaining time first. Shortest remaining time first algorithm is preemptive in the sense that when a new process arrives, so let me just read it from the slide. So while a job A is running, if a new job becomes whose length is shorter than the remaining time of job A, then B preempts A and B is started to run, right? So let me explain it using this example. Suppose we have four processes P1, P2, P3, and 4, and they arrive at time 0.0, 1, 2, and 3, right? And they have the bus time 8, 4, 9, and 5, right? Now let's have a look how their schedule will look like in terms of Gantt chart, right? So at time 0, we have, let me select the, so at time 0, we have no other candidate, only P1 is ready, right? So we allow P1 to run, but P runs once for only one time unit, and then P2 arrives at time 1, right? Now, unlike shortest job first, we will check how much remaining time of P1 we have. It is 7, right? Because it has executed for one time unit, so it has remaining bus time of 7 time units. The other process which is ready at time 1 is 4, is process 2, and it has the bus time of 4, right? Which is smaller than 7. So P2 will preempt P1, so P2 will be allowed to run. So P2 will run. So once it runs, the P3 arrives at time unit 2, right? So at time unit 2, what is the remaining bus time of P2? 3, because it has already executed for one time unit. What is the bus time of P3? It is 9. 9 is greater than 3. So still P2 has the smallest bus time, so we allow it to continue, right? So it continues at P3, at time 3, P4 arrives, right? What is the remaining bus time of P2 at time 3? It is 2 time units. What is the bus time of P4? It is 5. 5 is greater than 2, so we allow P2 to continue. So P2 continues, and finally it finishes. After executing for 4 time units, it finishes at 5, and then we see, okay, we are done with this one now. So now we look for one which has the smallest remaining time unit, remaining CPU burst, right? So who has the smallest? P1 has 7, P3 has 9, P4 has 5. So P4 has smallest, so we allow P4 to run. So it runs for 3 time units. So sorry, no, not for 3 time units. It runs for 5 time units, right? From 5 to 10. So P4. So we are done with P4 now. And then we look, okay, which one has now smallest? P1 has 7, P3 has 2, has 9. So we allow P1 to run for 7 time units. So it finishes at 17. So we are done with P1 now. Then we allow P3 to run, and it runs for 9 time units and completes at 26, right? So average waiting time. So what is the waiting time for P1? 0 time unit. It arrives at 0 and starts running at 0. So its waiting time is the, no, wait. So it's waiting. So waiting time, let's first look at the waiting time of P1. So here it doesn't wait anything. So it starts from 0 to 1, but then it is in this time period, P1 is waiting for its turn, right? So 10 minus 1, 9. After that, there is no wait from the perspective of P1. So the total time, waiting time for P1 is 9. For P2, the waiting time is P2 arrives at 1, right? It starts running at 1 and it completes here, right? So its waiting time is 0. It arrived at 1 and it started running at 1, right? See, it arrived at 1 here. P3 P3 arrived at 2 and it started running at time 17, right? So 17 minus 2, 15. Wait a minute. Wait a minute. Yeah, I think in the solution it is not written in order. Yeah, 17 because it started running at 17, but it arrived at time 2, so 17 minus 2 is 15. And for P4, it arrived at 3 and it started running at 5, so 5 minus 3, 2, right? So you take sum and divide by 4. So the average waiting time is 6.5 milliseconds. Any questions? If P2 would instead have been 7, would it have switched or does it finish P1 since both have the same bus time? If P2 would instead have been 7, what do you mean if instead would have been 7? You mean its bus time was 7?
Yeah, so if it would have entered at 7 instead of 4, right? So then when P1 would have gone into time 1, they would both be at 7, right? But then,
So yeah, so when both of them are like, let's say if there are two processes and it is the time when you need to decide which one of them you allow to execute. If both of them have the same bus time, you can pick any one of them. Round robin.
what? Oh, okay. So, because I'd assume since you're running a process, you'd stay with that process. But if it doesn't matter, that makes sense.
Yeah, I mean, it's up to you. I mean, if like you are running away the process and the newly arriving process has also the same bus time, let's say 7, so you can like allow the first one or the second one. It doesn't matter, right?
Okay.
In terms of implementation, it will matter definitely, but at the level of the algorithm, it does not. Because in terms of implementation, because you will need to do context switch. Like if you are running P1 and it has 7 time unit left, and P2 arrives and it has total with the CPU bus time of 7, and you say, okay, I am switching from P1 to P2, you are doing context switch, which means you are wasting the time, right? So it is in terms of performance, it is not efficient. But in terms of algorithm, it is fine because in the algorithm says that you pick the one which has the smallest burst time. So both of them have smallest, so you can pick anyone.
Okay. Makes sense. Thank you.
You're welcome. Any other questions? Okay, so example, assume we have the following processes. Find out the finish time, waiting time, and turnaround time of each process for the shortest remaining time first scheduling algorithm. Okay, so I am releasing the poll. Go ahead and do it. Week 9, day 1, quiz 9. Where is this one? Come on, guys. No one has answered yet. Just giving 15 more seconds. Okay. So again, do you want me to go to one note and explain? Okay, yes. Yeah, okay, okay. Again, let me just simply copy this thing. Okay. And day one, page two. Okay. So we wanted to do shortest remaining time first, right? So let me first simply note their arrival time. So 0, 5, 10, 15, A, B, C, D, right? At 0, I have no other competitor. So I allow A to run for 5 time units, right? And here I will be writing the remaining time, right? I'm just like writing here. It has run, it is remaining bus time is 25. Now at 5, I have two candidate A and B. So B has the smallest bus time, 20. So I allow B to run. So B run for 5 time units and then C arrives. So its remaining time is 15. So now I have three candidate A, B, and C. So C has the smallest, which is 12 bus time. So I allow C to run. So C runs for 5 time units and then D arrives. So here it is left with 7 time units. So now I have 4 candidate A, B, C, and D. C still has the smallest time unit, so I allow C to continue. So when I allow C to continue, it runs for 7 more time units and it finishes at 22, right? Make sure that my math is correct. 15 plus 7 is 22.
Yeah,
So
22.
yeah, thank you. And then C is done, right? So I can cross it out. And then I look at which one has the smallest bus time, D. So I allow D to run for 10 time units. So 32, right?
Correct.
And yeah, thank you. And then I look at which one has the smallest one. So the B has smallest CPU bus time. So 15, 32 plus 15, 42 and 47, right? So,
47. Yeah.
and here I have B. So now I am also done with B and I have only one candidate, which is A, and it runs for 25 time units. So 40 plus 20, 60, 67, 67 and 72, right?
Yep. Cool. I got it right.
Yeah. So now you can find like uh, wait time, turnaround time, finish time. Let's start with the easiest one, finish time. So A has finish time of 72, B has finish time of 47, C has finish time of 22, and D has finish time of 32, right? And turnaround, let's do the wait time now. So A has wait time of nothing here, and then it waits for this time period. 47 minus 5 is 42, right? B arrives at 5 and then it doesn't wait anything here, but then it waits in this time period, right? So 32 minus 10, 20, 22, right? C arrives at 10 and then it waits nothing. It doesn't wait anywhere, so its waiting time is 0. And then D arrives at 15, right? So it waits this time period, 22 minus 5, 15, which is 7, and that's it, right? Yeah. So in the same way, you can do the turnaround time. I don't want to like do it because it is taking time and I want to move on to the next slide. Is everyone fine with that? You have seen how to do the turnaround time in the previous example. Or you want me to do it?
Or I think from what you just showed, I think I understand it.
Okay. Is there anyone who want me to do the turnaround time? No?
No, I think we should be good by now.
Okay, okay. Then, uh, yeah, let's go to the next slide then. Okay, the next scheduling algorithm we have is round robin algorithm. So in this algorithm, each process gets a small unit of CPU time, which we name as time quantum or time slice. And that time quantum or slice is usually 10 to 100 millisecond. And after this time quantum has elapsed, the process is preempted and added to the end of the ready queue, right? So if there are, let's say, n process in the ready queue and the time quantum is q, then each process will get 1 by n of the CPU time. Let's say the total CPU time is 100, right? And we have 4 processes, right? So each one of them will get 1 by 4 of 100. So which is equal to 25. Each one of them will get 25% of the CPU time, but in chunks of at most q time units. So every time they get the chance to run, they will run at most for q time units. In this way, no process will wait more than n minus 1 queue time units. So let's say if there are 4 processes A, B, C, and D. So let's say A is waiting for B, C, and D to run, and then it will get its turn. So how many time it will wait? It will wait for n minus 1, which is 3 times Q time units. So shortest job first and shortest remaining time first algorithms, they provide better waiting and response times compared to the first come first serve algorithm, but they need mechanisms to estimate burst time. So the good thing about round robin algorithm is that it improves the response time just like SJF and SRTF algorithm, but it doesn't require any estimation mechanism for burst time. Why? Because it is by default assigning, a time quantum for every process. So it is scheduling based on the not based on the shortest burst time, but it is scheduling each process for a fixed quantum of time. So it don't need the burst time, the estimate of the next CPU burst time. So performance of round robin algorithm. So if the quantum value or the time slice is very large, so this algorithm becomes similar to first come first serve or FIFO algorithm, right? Because let's say if I make quantum Q very large, right? So what will happen? The first process which is running, it will allow the second process to run only once the first process has completed. Like let's say you have A, B, C, and D, right? And Q is very large, let's say infinite. So what I'm saying, I'm effectively saying first A will be completed and then only B will be able to run. Why? Because Q is very large. It is infinite. So it's mean that once the A is done with its execution, only then the B will get the chance. So which is basically saying same thing as first come first serve, right? And Q, so that's why we want Q value to be small, because then it results in good CPU sharing. Because if Q is small, I am not waiting for A to complete its execution. If let's say Q is equal to only 2 time units, so after 2 time units, process A will be kicked out, and the next in the queue, let's say B, will be allowed to run. So there will be good CPU sharing among processes. But if queue is very large, the sharing will be not good in the sense that B, C, and D cannot run unless A has completed its execution. However, queue should not be like too small. Why? Because if it is too small, then it results in too many context switches, which, and you know, context switches are a pure waste of time. So how? So let's try to explain it in through a diagram. So let's say you have a process, and the process needs 10 time units to complete, right? And let's say we are using the round robin algorithm with the quantum value or time slice value of 10 time units, right? Sorry, 12 time units, right? So quantum value is 10. So if you schedule that process, it takes only 10 time units. So even before the completion of its time slice, it already completes its execution. So there is no context switch, right? But now let's say that we reduce the value of quantum a time slice from 12 to 6, right? So we schedule the process. So it runs for 6 time units, and then its time slice or time budget is expired, right? So then the context switch happens. And let's say there, even if there is no other process there to run in the ready queue, only the there is one process, still the scheduler will kick in and it will check that, okay, is there any other process? If there is nothing, it will schedule the same process which was running earlier, right? But there is a context switch. Why? Because here your process is running in the user space, and then your scheduler kicks in, and scheduler is a system level code. So from you are first running user level code on the core, now you are running the scheduler, which is a system level code, to decide, because it will check ready queue and there is no one else, so it will say the process we can run again, but there is the context switch from user space to the kernel space, and then from kernel space back to the user space. So there will be two context switches, right? When you reduce the quantum. Now, if you go to the extreme case where you make the quantum value to 1, not extreme case, but like make it too small, let's say to reduce it 6 times. So what will happen? After every 1 minute, your scheduler will kick in and it will check, okay, is there any other process? Is there any other process? Even if there is not any other process, still there will be context switches, right? And you will have 9 context switches here. And after 9 context switches, your single process will complete its execution. So the issue is like, if your queue is very large, your round robin algorithm becomes effectively a first come first serve algorithm. If it is too small, queue is too small, then it incurs too many context switches. So we want queue to be a reasonable value. Okay, now let's have a look at the example. Let's say that we have the quantum value or the time slice value of 4, right? And we have processes 1, 2, and 3. The bus time of the first is 24, the second is 3, and the third is also 3, right? So how the schedule will look like in the form of Gantt chart. So at time 0, let's say all of them are ready at the same time. So all of them are in the ready queue when we start scheduling, right? So we pick the first one, which is P1, and we allow it to run for 4 time units from 0 to 4. And then this P1 will be put back at the end of the queue. So now the next one, P2 will run, right? So P2 will run for 1 time slice, which is 4. But the actual bus time of the P2 is 3. So it's mean it is completed at 7. 4 plus 3 at 7. So when it is completed, we need to make decision again who will run. So this is done now, right? So we have in the queue P3 and 24, but P3 and P1, but P1 is at the tail of the queue, right? Because it already had got its turn. Now P3 will then run for 3 time units in next time. So 7 plus 3 for one time for one time quantum, but its actual bus time is less than one time quantum, quantum, which is 4. So it will complete at 10, right? And then this is also done. Then we will make the decision. So we'll allow the P1 to run for 1 time quantum. So we should run from 10 to 14. And then again, there will be context switch. Again, there will be context switch, context switch, context switch. And finally, at 30, your P1 will complete its execution. So typically, uh, round robin algorithm has higher average turnaround time than SJF, or shortest job first algorithm, but better response time. Okay, now let's do an example here. During the final P1, is there still context switches? Are you talking about these ones? This one? Yeah, there are context switches. Why? Because remember, here, what is happening here? At here, you are saying, okay, I am allowing P1 to run. And when I say I, it means scheduler. Scheduler says I am permitting P1 to run for 4 time units. So it sets a timer, right? It sets a timer with a value of 4 and the value decreases, right? So when the value decreases from 4 down to 0, right? So scheduler again kicks in here, right? At this time point. And what the scheduler will do, it will check the ready queue. Is there any other process in the ready queue? It finds out no, there is no other ready process. So it will say, okay, now the P1 can run, right? But what is happening here is, so first your P1 code is running. This is user level code. I'm writing U only to indicate it, right? And consider that you have a single core, right? So when the timer expires on the same core, your kernel level code, which is actually your scheduler code. I'm writing S for that. Sorry, I'm writing S for that. Okay. So now scheduler will run and scheduler will make decision and it will see there is no other process. So it will say, okay, I'm running P1 again. So P will run again. So, but there is a context switch from P1 to S and then S scheduler to P1. So that's why there is a context switch. Any questions? If scheduler has access to ready queue, could you just check if empty is so continue running the same processor, or is that a modification to RR? Yeah,
Like, so
scheduler
that,
has access.
yeah.
Scheduler has access to ready queue, but the thing is, like, how can scheduler actually check the ready queue? By executing the scheduler code, right? Scheduler itself is a software. You need to execute its code. So you will execute its code on the core. And if you have a single core, so you cannot run P1 and the scheduler at the same time. So then that's why there will be a context switch. Or maybe I'm not getting
So
if your
yeah,
question is
so but
different.
during that check, is it still so if you were to check it, right, does that code, is it still expensive without the contact switch, if that makes sense? Because it still has to talk with the system, right? And it has to check in the code. Am I understanding that correctly? And then it
Uh,
goes,
no, you need to rephrase your question.
so it does the contact switch after every 4 time.
Time
Is that
units.
correct?
Yeah.
So if it has access to the queue,
Mm-hmm.
why not while it's empty, you don't have to do like you still have to check, right? You still have to check to
Yeah.
see if the queue is empty, but
Yeah.
if it checks and the queue is not empty, there's no reason to do a contact switch because you're using the same process.
So
Or am
you
I
are
not
saying
understanding
if
correctly?
the queue is empty, if the queue is like if you are saying, okay, why we are checking the queue again and again when we know that there is only one process there, and why even there is no point for scheduler to go and check it, right?
No, no, but you always have to check, right? Because you don't know if another process is going to be
Yeah,
added. Right?
yeah,
But what if you like you can continue to check, but you don't have, if it's empty, there's no reason to do a contact switch. Does that make sense?
yeah. If it is empty, means there is no other waiting process. So it's mean
Yeah.
you don't have anything to run. So
So
process
so
dead. You
all
will
you would
just
have to
keep
do,
monitoring. You will just keep monitoring if there is until another process becomes ready to run.
yeah. And so is that what this is doing, or is there still a contact switch at 14 and 18 or 22?
No,
Does that make sense?
no. Here the queue is not empty. Here the queue is not empty. Sorry if I'm not able.
Even at 10? No, at 10 the queue isn't empty anymore.
No, queue is not empty. Why? Okay, let me do it again here. So yeah, wait a minute.
Is it because P1 is still considered being in the queue?
Yeah, yeah.
Okay.
Do you want me to
That
go
makes
to
sense.
one note or
No, no,
you
no, no,
got it?
no, no. That makes sense to me.
Okay. Yeah, because every time when a process when the time slice of a process is expired, that process is put back into the ready queue at the tail on the tail of the ready queue.
Okay.
So at 14, P1 is done for 4-time unit, and then it is put back in the ready queue on the tail of the ready queue. So then schedule will go and check, is the ready queue empty or not? No, it's not empty. P1 is there.
Okay, yeah. I guess what I was saying is like why is there a way to possibly make it so it just continues running the process without having to put it back into the queue, but that's not how it works.
No, because
Okay.
you have to put it back because you don't know why maybe there is another process
Yeah,
already arrived and sitting in the ready queue to be for its turn, right?
makes sense because if you make that assumption, then more processes come in, but then you're continuing to work on the longer process possibly.
Then
Okay,
you are
that makes
like,
sense.
if you are continue P1, then you are making other processes to wait for longer time.
Makes sense. Thank you.
You're welcome. Did we do this example? No, we didn't. Okay. I don't know. Time flies. Every day I'm saying that I'm telling myself today I will complete my slides, but then when I come to the actual lecture time, I am like short on time. Maybe I don't know and how to speed it up without compromising your understanding of the material. Okay. Okay, here we are we need to let me first find set here quantum is equal to 30 time units. Okay, and what we need to do, finish time of each process, we need to find the finish time of each process. Okay, so basically we first need to do the schedule, right? So let me first write their arrival time 0, 15, 25, 35, 55, right? Okay, so this is A, B, C, D, E, right? So this runs for 30 time units. So A runs from 0 to 30, right? And then, okay, I'm here also making the ready queue, right? So the ready queue at time 0, it is only A, right? Now ready queue at time 30. At 30, I have what in which processes? B, C, and A, right? Everyone with me? If something is not clear, please stop me because it is more time consuming when I need to come back and then explain everything from start again. So I'm putting A on the at the tail of the queue, and B and C they have already arrived here. See, B and C, right? So now we will run B for 30 time units, right? So 30 plus 30, what is the, okay, and also we need to, let's say I'm making a one more column, which is remaining time, okay? So A has run already for 30 time units, so 10 time units are left, right? So now we run B for one time, for one quantum. So, but B's time, bus time is 25. So it will run only for 25 time units. So 30 plus 25 is 55, right? So its remaining time is now 0. So in the meantime, at 35, the D at the time unit point 35, D entered the ready queue, right? And E also entered the ready queue at 55. Now B is done, right? Because its remaining time is 0. We look at the first next one on the at the head of the ready queue. It is C. So what is the bus time of C? 30. So it runs for 30 time units. So 30 plus 55 plus 30, 85, right? And its remaining time is 0, right? So it is not put back in the ready queue, right? Now the next one is on the head is A, right? So A is again allowed to run for 30 time units, but its remaining time is 10 only. So it is done at 95, right? So here we have remaining time is equal to 0 and we are done with A. Now the next is D. So D is allowed to run for 40 time units and its bus time is 45, right? So 95 plus 40 is what? 135? So it has 5 remaining time units. And then it is put at the back of the queue, right? And then E is allowed to run for 30 time units, but its bus time is only 25.
Or,
So
sorry, wouldn't it have 15 remaining time units because it's 45?
yeah, so 45 minus, thank you.
Minus 30 would be 15.
Thank you,
Okay.
thank you, thank you. Yeah, but is this correct? 95 plus 30.
I think
No,
I think it's
125.
25.
125, sorry. Thank you for correction. Okay. So then E is allowed to run, but for 35 time units, but it is only 25. So 125 plus 25, 150. So now it has 0 time units left. So it's removed, and then we run D again for 15 time units, so 165, right? So finish time, we had to find the finish time of all the processes, right? So the finish time of A will be A completed at 95, B completed at 55, C completed at 85, D completed at 165, and E completed at 150. Okay, is that clear to everyone?
Yeah, that's very clear.
Okay, good. Then, okay, then I'm releasing the poll. Go and do it. Quiz number 10. Okay, you have 120 seconds. Everything is same, only quantum value is 10, not 30. Okay, so okay, now for this, do you want me to do it on one note or we are fine? If there is even a single student who says want me to do it on the one note, I will do it on one note. Yes, sir. Okay. Okay. Okay, so Q is equal to 10 this time, right? And again, here here I will write the remaining time. So 0, 15, 25, 35, 55, and okay, A, B, C, D, E, and here I'm writing ready Q, right? So at time 0 in ready queue, I have only A. So I allow A to run for how many time units? 10 time units, right? So A, and then at 10, I still have no one else in the ready queue. So A is placed book back in the ready queue, right? So like, you know, like this, right? So at 10, I have no other candidate. So I allowed A to run again. So it runs for 10 more time units. 10 to 25 here. Maybe I should use a different color now. So A again, and but at 15, we have uh, B entered in the ready queue. So at 25, A is removed from the head and put it at the back, right? So sorry. So before A, at 25, we also have C entered in the queue, and then we have A here. And it is up to you because at 25, you are also putting A back in the queue. So it could be like BAC or BCA. It doesn't matter because
A,
both things are happening at the same time.
A will end at 20.
Sorry?
A should end at 20 instead of 25 because you're adding 10 to its original 10.
Oh, okay, okay, okay. Thank you, thank you. Yeah, 20. Okay. And yeah, so how much time now? A is remaining time of A is 20, right? Now at 20, then we need to yeah. So if it is 20, then we don't have the C has not yet arrived here, right? So we have only B and A. Now at 20, we pick the one which is at the head of the queue, B, right? And we allow it to run for 10 time units. So 20 plus 10, 30, right? And then we put it back in the uh, so but at time 25 the C has already arrived, and then at time 30 we put B back in the at the end of the queue. So we have ACB, right? Now at time 30 we pick the one which is at the head of the queue, which is A. So we allow A to run for 10 time units, so it becomes 40, right? And its remaining time is now 10, right? But at 35, D has arrived. So D is in the queue, and at 40, the A is put back in the on the tail of the ready queue, right? I'm just writing ready queue again here because to clear up the things C, B, D, A, right? So now at 40, we pick the one which is at the head, which is C, and we allow it to run for 10 time units. So I'm writing here 50, right? So 20 time units are left for C, and then C is put at the back, right? And then at time 40, we pick the one which is at the front, which is B, and allow it to run for 10 time units. So 40 plus 10, what is happening here? Yeah, now this is problematic. So it should not be. Let's say this is 50 here, and I am writing 55 here, right? No, guys, sorry. So 50 plus 10, 60s. So I need to undo this. Yeah. So yeah. But then at 55, the E arrived, right? And then at 60, the B is removed, right? And it is put at the tail. How much time of the B we have left with? 5, right? Then at 60, now we pick the one which is at the head, which is D, and allow it to run for 10 time units, right? So 70, and here we are left with 35, right? So now we move D at the end, and then we pick the one which is at the head, which is A. So A runs for 10 time units, 80, and here A has 0. Now we are done with A. Okay. Then we pick the one which is at the head, which is C, and we allow it to run for 10 time units, right? So it run until 90, and remaining time is 10. And then we put C at the back. Then we allow E to run, and for 10 time units, so 100. So it becomes 15, and E then moves to back. Guys, do you want me to complete this one? You got the idea how the things are working, right?
Yeah, we got the idea. I feel like it will take
Yes.
much
Yeah,
longer.
it looks like it will take forever to complete this one. So because the quantum value is too small, 10, right?
Hmm.
Yeah. So you can complete the rest of this example on your own. Okay. Okay. So let's compare round robin with FCFS in terms of performance. So remember, some of the performance parameters are the response times and the turnaround time. So round robin is good for fast response times, but it is not good for low turnaround time. So here is an example. Suppose that you have 3 jobs, and A, B, and C, and all of them arrive at time 0, and each has a CPU burst equal to 10. Now, if you use round robin, how it will look? So if all of them are arriving at the same time, so you will first allow A to run for time units. So A, B, C, right? And then they again, because each of them take 10, so each of them will take one more turn, A, B, and C, and then you are done. So now what is the turnaround time for A? So the turnaround time of a process is the time when it becomes ready to the time where it is completed. So A became ready at 0, right? And it completed at 20, right? So its turnaround time is 20. And what is the turnaround time of B? It was ready at 0, and it completed at 25. And C, it was ready at 0, and it completed at 35, right? So these are the turnaround times of A, B, and C. Now let's do the same thing, scheduling using FCFS, and see the turnaround time, right? So if all three of them arrive at the same time, so like A, B, and C, they will go one by one, because this is first come, first serve. So A, then B, and then C, right? So what is the turnaround time of A? It is 0 to 10, right? What is turnaround of time of B? 0 to 20, and of C 0 to 30, right? So every process here, A and B have lower turnaround time than A and B in the round robin scheduling algorithm. So on average, the turnaround time for FCFS will be lower, and turnaround time will be higher for the average turnaround time for higher will be higher for round robin scheduling algorithm. So a round robin algorithm is not good when if you want to optimize or reduce the turnaround time, but it is good when you are more interested in fast response time. Why? Because you know you process C doesn't need to wait for the completion of A and B before it gets its done, right? Here. But here, so that's why response time is low in case of round robin algorithm. However, response time is high in case of uh, first come first serve, because C can be scheduled only after A and B. Okay. Any questions? I will stop here, but if you have any questions, let me know. No? Okay, if no question, then that's all for now. But before leaving, just one statement. Today, I was supposed to release your Project 3 Module A. I don't, according to my time, I will be able to release it tomorrow morning. Okay. So, yeah. And it will be about scheduling algorithms. So, yeah, cover these slides carefully to understand. Okay. So that you will be able to do the project 3 module A. If no questions, then that's all for now, and see you on Thursday.
Thank you.
Thank you, everyone. Have a good day. Bye.